Yes, so now if you just look at this equation for a while, you may recognize this form of equation from your earlier courses on transport phenomena if you solved any problem in the cylindrical coordinate system. You would also recognize it from your elementary courses on PDEs if you have done such a course. So it turns out that this equation is actually a form of the Bessel's equation, and so it can be solved analytically in terms of the Bessel's functions. So I'll just write out that solution here. So it's a standard thing to do if you look up a mathematics handbook like Abramovich and Stegan, and you look at the standard form of this equation. You can bring this equation into that standard form, identify the corresponding terms, and write out the solution analytically. It's also something that if you plug into a software like Mathematica will throw out the Bessel's function analytical solution. So I'll just write it down here because it's not really our focus right now. We're not super interested in deriving that formula, and it's something actually that is pretty much available easily, like I just mentioned. So here J naught is the Bessel's function of the first kind of zeroth order, and the argument of this function is Rw over I to the power half times R, and as a normalizing factor which accounts for the boundary condition, no slip boundary condition, I have the denominator coming in this form. Okay, there we have it. Typically, the Bessel's function also involves the solution to this Bessel's equation involves a Bessel's function of the second kind, y, but that diverges at r going to 0, and since we need it to be bounded, we set the coefficient of that second homogeneous solution to 0. And so the final analytical solution is written here. Let's call this 4. So this is the full analytical solution to the problem for arbitrary r omega. Of course, this is just for the companion problem. So now remember that u, right, is the imaginary part of u hat, which is e to the power I r omega t times h. But now we have a problem, right? How do we extract the imaginary part analytically? Right, so we have written down the solution analytically in a formal way of the companion problem. In principle, if I can extract out the imaginary part of this term multiplied by e to the power I r omega t, then I'm good to go. However, the problem is that you have an I sitting inside the argument of the Bessel's function, and the Bessel's function in general has no simple analytical form. So unless I actually substitute in specific numerical values for r and then simplify this whole thing to just a complex number, I cannot actually extract out the imaginary part. So while I can numerically plot this solution by substituting different values for r, finding out the complex number and taking its imaginary part as u, I cannot get any physical insight from that because I can't write down an expression for the velocity. What is possible, however, is to look at Taylor series expansions really for the Bessel's functions in the limit of small rw or large rw, that is asymptotic expansions in either limit, and then I will get a simplified expression. So if I want to gain insight from this formula, the only thing I can do is to look at limits in rw. But rather than do that here from the analytical solution, we are now going to directly obtain, right, a perturbation series solution to u for large and small rw. Okay, so by using the perturbation method. So to reiterate, having obtained this companion problem and all of this being done exactly, we can actually obtain an exact analytical solution to the problem in terms of Bessel's functions. However, that is a complex function, complex in the sense of complicated to analyze, and so we cannot gain much insight from having this analytical solution really. And so one option is to get this exact solution and then use Taylor series expansions and expand it out and then try to get an expression in limits of small rw, for example. But rather than go through this route of solving the exact solution and then expanding it out, we'll directly analyze this problem 3 for limits of small rw or large rw and directly obtain an expansion for the solution in series as a power series of rw using the perturbation method that we have been studying over the past couple of lectures. Also, using this approach is more instructive for our purposes because such an approach is applicable even if this equation 3 were nonlinear. And so since the entire goal of this thing is really to illustrate the use of perturbation series, this is what we're going to do now. But what I'd like you to bear in mind is this example shows you that perturbation series are useful not only if you have a nonlinear problem that you cannot solve analytically. They can also be useful when you have an analytical solution, if that analytical solution is too complex to gain any physical insight from, right? Like if, for example, we don't really know what Bessel's functions look like intuitively, the way we know how sinusoidal functions or algebraic functions behave. And more importantly, this is Bessel's functions with a complex argument, and we need to extract out the imaginary part of that. So it's really too difficult to get any insight from the formula 4. Okay, so with that in mind, let's now focus on obtaining perturbation series solutions to equation 3. So we really have two limits, like I said, large and small rw. So let's begin with the limit of small rw. Which is the small frequency. Now we know that this small frequency limit, we expect it from our earlier scaling analysis to have a predominantly in-phase response. To have a predominantly in-phase response and to behave in a sort of quasi-static way that is like Hagen-Poiseuille flow but modulated with the oscillatory pressure gradient. But we also expect some corrections which are out of phase because of the fact that Rw is not exactly zero. It's small but non-zero. And it is those corrections, out of phase corrections and maybe even in phase corrections for finite Rw that we want to calculate using the perturbation expansion. So let us now proceed with that program by assuming a perturbation form for the expansion. So for convenience now, let me just rewrite the equation 4. Right, this is just, equation 3. So I've just rewritten equation 3. It's the same equation. And now I'm going to assume a perturbation power series. Right, looking at the form of the expansion, it's reasonably clear that a good guess can be H0 plus RW H1 plus RW square H2 and so on. So I'm going to drop the third order terms and higher, and let's retain only terms up to second order. So the next step, of course, so let's call this 5. Right? And I can now substitute 5 into 3. Right? To obtain equations at each order. Remember, my boundary conditions are quite simple. They're just h equal to 0 and h being bounded. So that translates across all the different orders. So H0, H1, H2 and so on will all be 0 at r equal to 1, and they should all be bounded at r equal to 0. So the boundary conditions are simple for each order. Now the governing equation can be obtained also rather simply. The equation for H0, remember, is just the same as equation 3 if Rw are exactly 0. So the order of Rw 0, the 0th order problem, right, equals minus 1. And now we can solve this actually really simply by just direct integration, right, because this is a nested function. In fact, we could see that here itself, which immediately motivates a perturbation series, right? So even if you were to look at equation 3 mathematically, in the sense that someone were to present you this equation and say, look, I've obtained this equation from some physical problem and I want to obtain a solution to this problem analytically, you can, or you want to get some insight into the solution. Being an expert in perturbation methods, you should look at this problem and say, hey, look, if Rw can be small, or is Rw is assumed to be small, I can drop this term here, in which case I just have 1 by r dou by dou r dou h by dou r, which is a series of nested derivatives equals minus 1. And I can solve for h directly by multiplying by r integrating divided by r integrating. So you can get a simple analytical solution if only this Rw is taken to be 0. And so that should immediately motivate you a perturbation series, because if you solve the first problem this way, then the next order problem is going to be the same but with a forcing from the lower order. So at every order you should be able to solve the problem, as we shall see, by doing just direct integrations. So you should always have an eye out for such parameters, and over time as we do these examples, develop a feel for when you can use perturbations to get approximate solutions. Okay, so let's come back to the order problem for H naught. So if I'm going to do this, I'll do it in a slightly messy way right here. Okay, so if I take r to the other side, I'll get minus r. I can now do one integration, so I'll get minus r square over 2 plus a constant, let's call it b. I can now divide throughout by r, so I'll get r to the power 1 and b by r plus plus b by r. I now do the last integration, so I'll get r square by another 2 factor here. This term comes b logarithm of r plus c. So this is my solution. Now if I apply the fact that h naught should be bounded at 0, I must have b going to 0, right, because h naught is bounded. And correspondingly, because h naught must be 0 at r equal to 1, c must just be equal to r square over, c must be equal, so if r is 1, this side is 0, this side is just minus 1 by 4, so c must be equal to 1 by 4. So therefore I can say that h naught is equal to 1 minus r square upon 4. So this is your 0th order problem. Now let's move to the first order. So if you look here now, I'll get a minus, so this term will basically pop out an Rw with h1 here, right? This minus 1 which I had earlier is not going to have any contribution because it's the leading order. So at Rw, the right hand side is just 0. But I have a term coming from here. So Rw already exists. So the only way I can get a first order contribution is if I replace h with h naught. So here I'm doing it quickly because it's a relatively simple equation. But you can just substitute this inside, expand the whole thing out, and you should get the same result that I'm getting. But after a while, you will see that these things are pretty easy to track. So the first term just throws out dou h1 by dou r, right? Being linear in h, I just get the term of the corresponding order. Now this will, like I said, if I had h naught here, it's an Rw term. If I put h1 Rw, I'll get an Rw squared term, right? Which it would actually come for this next order. So I don't have an h1 contribution. So the only contribution from there is minus I times Rw h naught. And this must be equal to 0 because there is minus 1 gives you no contribution at order Rw. So therefore the equation is 1 by r dou by dou r of r dou h1 by dou r is equal to I times, so this is at order Rw, so the Rw is factored out, right? So there is no Rw here because the Rw is factored out to get this equation. So it's minus I times h naught. So it goes to the other side and I get 1 minus r square by 4. Now again, you see the form of the equation here is identical to the form I had at 0th order. Only that the forcing term, instead of being minus 1, is now I h naught. So I can again solve this problem by direct integration. And in fact, if you go to order of rw square, you will get, I leave this for you to do as an exercise, but you can almost anticipate it from the previous developments. Right? If you go back here, again this will contribute nothing. And here I'll get h1, because of Tartuni way I can get an r omega square term. It'd be I h1 instead of I h naught. So by solving this equation for h1 and then solving this equation for h naught, this equation for h1, substituting it in here, I can then solve it for h2, and in fact so on and so forth. I can build up the perturbation series solution. But we'll stop at second order, and I'll leave it to you to do these simple nested integrations and just write out the full solution for you, so that we can proceed with our analysis. So you should be able to show that h1 is just three by 4, and h2 is as follows. Right, at every stage applying the boundary conditions of h1 and h2 being 0 at r equal to 1 and being bounded at r equal to 0. That should be a simple calculation. Okay, so now we have the perturbation solution to h up to second order. We now need to substitute that into this, of course, backward relation multiplied by e to the power I r omega t and extract out the imaginary part, right? So now u is equal to e to the power I r omega t. So here we can write it in terms of cosine and sine. Right, times the solution for h, so which you will have h naught, right, plus rw times h1, which is I by 16, let's make this curly braces, plus of course rw squared times h2, and then I take the minus sign inside, okay. So now if I want to write the final solution for u, right, this is, remember, in the limit rw being much less than 1, my solution for u, which is now the actual solution of the oscillatory field, right? This part of the problem is the companion problem. This is u hat, my bad. Yeah, so u hat is e to the power I r omega t times h, and now the actual solution u is the imaginary part of u hat, right, which means I need to extract out the imaginary part from here. So this cosine r omega t is real, but I also have an imaginary part here standing in the h solution. And because sine omega r omega t is imaginary here, I should multiply it only with the real part of h. So let's first look at the terms order by order. So first of all, I'll get sine rwt. Remember, so this is, remember, the in phase. This is in phase response, right? This I, when I multiply it throughout, it will keep the term imaginary provided I multiply it with only the real contributions from H. So I'll get 1 minus R square by 4 here. And this is also just the first order term, right? There is no contribution from cosine R omega t times 1 minus R square by 4 because that's real. Now at the next order, which is this term, remember this term is now imaginary, so I should multiply it with cosine R omega t. Right, times 1 by 16 into stuff in the bracket. And then I have the second order term, which is this guy here. It's real, so it should multiply sine so that the combination is imaginary and contributes to the solution u. And now the factor from H. And this is our solution for U. In, of course, the limit R omega is much less than 1. Okay, so here we have now a beautiful formula that we have obtained analytically now by using the perturbation series expansion. And as you can see, it has, we will soon see that it gives us much more insight than the Bessel's formula. So what can we learn from this solution now that we have obtained? Well, first off, we see that the leading order term, which means if I were to set R omega exactly equal to 0, the main contribution comes from an in-phase response, sine R omega t, and the radial component of this is parabolic. So this term, this first term here, right, is actually just the quasi-static response. Right, so it is just really a parabolic Poiseuille flow, but whose amplitude is modulated exactly to match that of the driving pressure gradient. So it's as if you solved the original problem like you would solve Hagen-Poiseuille flow, neglecting the time unsteady term and just solving it directly. In fact, it is a solution you would have obtained if you took Rw equal to 0 in the scaled version of the problem where R omega is much less than 1. Basically, in this problem, if you set R omega going to 0 and you solve the remainder, you will get a solution. And you can see this f of r is 1 minus R square by 4. So that is, of course, you could have got this first term of the solution just by setting Rw equal to 0 in the appropriately scaled problem. This is the sort of thing we did earlier in our scaling analysis. But now by using perturbation methods on that scale problem, we see that we don't just stop here, but we can get corrections to the quasi-static response for finite values of Rw, albeit small values. So we see that the first order correction, right, after the leading term, the next most important term which gives a correction is now out of phase. So you can see the effects of inertia, the fact that you've not completely neglected du dt, comes into play to give you a kind of lagging in the response of the velocity. And you get cosine R omega t multiplying the first order term, and you get some variation in the radial direction, which is now non-parabolic. Of course, it has to be even in R because of the nature of the problem being axisymmetric. We now go to the next order and we again get a in-phase, this time correction at order R omega square, and with a more complex radial response. And if I go to R omega cube, an odd order correction, you will again get a cosine R omega t. Right, and this becomes clear if you, in fact, because you can see this as I, the first order part of H had I, therefore you got cosine. The second order part had was purely real, so you pulled out only sine. The third order, because you would have substituted it by writing IH2, and H2 is real, you will get the third order term for H to be complex, and therefore you will pull out a cosine response again, and so on. So by looking at the form of this, you also have insight now that tells you that the leading order behavior is in phase, but then the correction is out of phase, then you have another correction which is in phase, then you have another correction which is out of phase, and so on. So this is how the problem unravels itself and really shows you a combination of in-phase and out-of-phase responses which we had expected. But it also reveals that the leading behavior is really in phase. Okay, now apart from just this kind of insight that we can get by just examining the form of the solution, it's of course rather simple to plot this solution and therefore get some further kind of understanding of the behavior, some more visual understanding. So for that, let me pull up a Mathematica notebook where I've done just that. So you will see here that I have simply basically written out the solution we have just described. U is the full solution up to second order in R omega, and U naught, let me just magnify this. Yes. So U is the full solution we've just derived. U naught is the solution if I take only the leading order quasi-static response. So this is what you would have got without using perturbation if you just set RW0 in the scaled equation. Right, and I now plot it here, and the blue line corresponds to the full perturbation solution, so you can think of this as the full response, and the red dashed line is quasi-static behavior. So if I vary time over, I'm going to do this over 2 periods of motion. Here, let me just play it for you. Yes. So you first look at the blue line, you see it's just, as we expect, oscillatory. And if you compare it to the red dashed line, you see it's almost a quasi-static response to the driving sinusoidal forcing. But there is some amount of lag that really comes from the fact that RW is finite. If you make RW much smaller, you will exactly overlap with the red dashed line, which is the completely quasi-static response. So this is what you would expect to see. You see, as the pressure gradient goes forward, you tend to lag, the velocity lags behind it. Let's pause it here. Right, so as the pressure gradient swings forward, the fluid goes in the positive z direction, but the true response lags a little behind the quasi-static response. It ultimately catches up to it at 1/2 period, but then the pressure gradient reverses. The fluid again lags behind. Right, so now when the velocity is quasi-static velocity is more negative, the real velocity is not as negative. Again it catches up, again it begins to lag behind, and so on. So this is really the behavior that the system shows in the small frequency limit, which really looks parabolic most of the time. It's almost quasi-static, but there is just some lag that arises as a correction due to finite RW. Okay, but really the behavior is more or less close to parabolic and what you'd expect. With that, we now turn to the more complex and less understood problem, or the less intuitively understandable problem of the large frequency limit. So what happens if the pressure fluctuations are incredibly rapid compared to the response time of the fluid? Will the fluid just stay static? Or that seems unlikely, but what would the response be like? Certainly, one feels that it won't look anything like a parabolic flow.